Yeah, we can see your slide.
Okay. Let's see. Yeah. Well, one second. So yeah, I think this is my second time, right, with IChemE song, and with is 101 as well, presenting this type of webinar. So for today's session, I picked this title simply because that's one of my hobbies basically. So it's about how we implement our specialization within our chemical engineering realm, which we call like process system engineering. And then I'll discuss a bit briefly on what it is, and then I will then share something about some examples in the past that I've done with some dummy example. Yeah. This is the one that I've because I'm now representing myself, not anybody else, not any company. So everything that I'm going to present to you solely based on my own experience. Some resources that I think are going to be useful if any of you would like to read about this topic further. So I have these books, and then I've read some of these articles as well, and then these are things the three articles that are relevant for today's discussion. Okay, so what is process systems engineering? So process systems engineering, or PSE, is about if we have like if we have like a system, and where we have like some physical processes or chemical processes, and then we want to model it with mathematical language in such a way that we can do something with that model, right? So that something is if we want to make it like a design. So typically, if you have like a problem, and we have a chemical A, right? And then we want to make chemical B, and then we can then devise or develop a process in such a way that we can then design the whole system. And then this whole development of the process, we model it mathematically. Some of us, we typically use our like process simulation software to do so. Hence, we don't see exactly what's behind the scene, but nonetheless, that's one of the things that we do. And then once we get the model, right, so we can do a lot more with that. So we can do some sensitivity analysis to see which variables are more important, or which variables are affecting the performance greatly. And then we could also do some optimization to maximize the profits, or minimize the cost, or minimize the waste. And then we could also do some control if we make like a dynamic model as opposed to steady state model. So I think I put this from this article just to share with you a little bit on if we have like a reality. So this is how I understand this graph. So we have this reality. So your experiments and your lab, and then the plant, and then we know there are certain variables affecting the performance that we would like to evaluate, and then we could do like what we call experiments or design of experiments to make it much more efficient. And then we do some of these experiments, and then we see if the results is aligned with what we would like to have, right? And then on the other hand as well, if the experiments is too expensive to be done, and then yeah, either it's expensive or it's not possible to be done because it's a running plant that we cannot do any open and close valve as much as we want. So we can make a model for that plant or for that system, right? Which we call it now virtual reality or digital twin nowadays. They use digital twin term. And then once we make the model, and then we make sure that model is in agreement with the situation in the plant or in the reality, and then we can then use the model to do any virtual experiments, right? The things that I mentioned about the sensitivity analysis or optimizations, things that we can do with the model. And then once we get the optimum solution from the model, and then it shows us that we have to open this valve and that valve, and then we can then verify the results of the optimization model with the yeah, I mean the real situation. And then we could do a lot of other analysis. Yeah, so that's how I understand this diagram. And another diagram is that because now we start to see that we need to have like a mathematical modeling and optimization, and then we use this tool to support our decision making process in terms of like I mentioned on the raw materials A to make raw materials to make product B. That means we need to be we are going to face different options, right? Do we want to make like a CSTR type of reactor, or a fixed bed type of reactor, or do we want to make or to use like a distillation column, or do you want to use like a membrane type of separation, or just simple flash? So all of these things, they require decision making. um, and it's still the same from the same article. So I think what I can understand from this diagram is that we have this a process that we model, right? We have a mixer, reactor, separator, and a splitter. And then from the left to right is more on the resources that we put into the process, and then the products and the wastes that we get out of the product, out of the process. And then these resources will then come from a different locations, and then it has some different availability. It has also some demand requirement for it in for different processes or different plants. And then from the product side as well, we need to be able to improve the quality of the product. We need to reduce the waste, right? And then all in all, if we see from the top, from the very left to the very right, we will deal with a different scale, right? So this is like a process scale, and then from end to from the left to the right, we will be dealing with the where we are going to get our sources, our raw materials, and our energy, and then up to the right, and then how are we going? I mean, yeah, I mean, what's the quality of the product, and then can we make it more efficient in terms of the lowest waste, or maximum efficiency, or maximum profitability, and and then so at different scales. And then this PSE stuff, it's also and then the whole math and modeling and optimization stuff, it relates strongly with the what they call like a multi-scale modeling. So it touches many different uh, engineering fields, right? And then it also affecting a different type of applications on this diagram. um, and then basically, once we get that model to support our decision making, and then how do we make decisions basically? So typically, if we have different options, we have like option one, option two, option three, so, and then some other options, right? And then we can then put some criteria to differentiate these options. And then in this criteria, and then we evaluate then option one against criteria one, it scores like, I don't know, 10, maybe 15 or something. And in option two, it will then be it has some numbers on this criteria one. And the same thing goes to option three. So we can then fill in this table in such a way that we can then I mean the criteria is such as such that we can differentiate all of these options, plus and minus. And then we can also then afterwards to pick which of these options is then the most beneficial for our from our perspective, or most, yeah, I mean the ones that we prefer more. We can then like a weighted KPI. We can make weighted KPI, so we can then put emphasize more on criteria one, or criteria two, or criteria three, depending on what application that we want to see. And then we can then see, okay, so option two is then the most profitable one, for example. Yeah. Um, and then we can do this if we have like a limited number of options and a limited criteria. We can simply solve this in Excel. We can make this table in Excel. But then if we have more than so many options, and then it's also including combinations of options, and then we have lots of criteria, right? Lots of calculations to get to that criteria number. That's where we need to have a lot more elaborate tool to help us to get some decisions. And it's also like if we have some uncertainties into the systems, right? If we have like a variables like those resources that we saw in the previous slide. So if the resources are not really stable, and then some uncertainties because of the, I don't know, seasons, maybe because of the situations. So there are some uncertainties. So there is the situation where we need to have something much more elaborate. Um, so mathematical modeling optimization, in its roots is that we need to solve a specific goal or to optimize a specific objective function. Yeah, it's either typically it is either maximizing profit or minimizing cost. And then we have like a set of constraints. So it can be like equality or inequality. So equality constraints, in at least in my understanding, is more like if we have like a mass balance. So what comes in should be equal to like what comes out, right? So that's a simple equality constraint. The same goes with the energy balance. And then some design criteria, it can also be like either equality or inequality. For example, we need to have I don't know, maybe a pressure drop of less than half a bar or 1 bar per 100 meters, for example. So these are like another example of inequality constraint. It's also like some rules and regulations. So we should design our plants to meet at most a certain sulfur level or a certain CO2 or NOx emissions, things like that. So this is what we call like a. This is basically the model of the system, right? Either it's a chemical plant model or any other mathematical models to support business decision making. So things like that. And then we have what we call the one that we want to see what the optimum results are, or what we call it like a decision variables or independent variables. So things that we want that we can open and close, things that we can pick and select, things like for example operating conditions. What is then the temperature that we want to operate that reactor? What is then the flow rate, the pressure? Do we want to have like one big reactor or two small reactors in series? Do we want to have like either membrane separation or a flash vessels? So these are the decision variables or the independent variables, right? We can make all of these models, but then if we go back to the yeah, just to set some baseline, yeah. So mathematical optimization, I put like mathematical optimization in one page. So there are like, as far as I understand, there are two highways to solve this. Number one is then what we call like a gradient based, so it's based on the Newton approach. And then the second one is what we call like a stochastic optimization. It's more like a trial and error, if you want to say so. So it's suppose that we have like a graph like this, x squared or 3x squared, right? And then this is the function, and we want to find the minimum value of this. So if we can see it, like in this case, we have the x-axis as the independent variable and then the y-axis as the dependent variable. If we can see it like this, we know for sure that this is then the at 0, x equals to 0, that is then our minimum value, right? But mathematically, how do they do that? So mathematically, they do it by gradient. So they derive this. So 3x squared is derived into like 6x, right? 6x. And they say if they say like the necessary condition for this to have a minimum point, optimum point, sorry, it has to have like the first gradient equals to 0. So this is this is then the gradient. So this when this gradient is at 0 point, which is in this, that's the optimum location. Yeah, that's the optimum location. But then how do we know whether this is minimum or maximum? And then they go one step further, which then the second derivative. Yeah, and then what they say like a sufficient condition. So if the second derivative is like a positive in this nature, like in this case, so 6x, you derive it one more time, it's 6. So it's a positive number. So if it's a positive number, that means it is a minimization problem. So then we will find a minimum point. And we can confirm it here because we can see it, right? That's how they derive the theory. And if it's the other way around, if this is then minus like that, and then we will have a maximum function. You can try this later at home. The second one is that well, it's so difficult, right? I mean, when we build this model in HiSys or in any other software, for example, it's very difficult for us to know or to get a graph like this or to make an explicit function. So what we do and what we could do is that we simply throw a bunch of x values, right? So in this case, like x minus 2, what is then the y? Y is then 12, and then if x minus 1, what is then the y is then 3, and so on and so forth. So we can just throw a bunch of values, and then from here we can see where is then the minimum y, right? In these 5 numbers, y is then equals to 0 when x equals to 0, right? So you can see this is another like pathway. But there are like a downside here. See, suppose that we miss this, so we don't know whether it's x is like zero. Maybe we throw a bunch of like x equals to a half or x equals to minus half. We may not be able to see the absolute minimum. I mean the global minimum value. But that's okay. I mean, as long as we know among these options or x, right? So we can see at least we have the lowest. We have a lowest number. That's the second highway, and then this could also be like we it could also be like we combine these two methods, right? The gather and base method and then the trial and error method. So and then you get into the discussions on the whole mathematical optimization study. So I just leave it to you. I just leave you with this to have some basic. And this is like a one-dimensional problem, right? It's only like one independent variable. And then if we have like two independent variables, we have like for example the this horizontal and then that this length and then that length. We can see, and then the objective is on the z-axis like this. And then if we have this Himalaya mountain, we can see this local maximum, and then this is like what we call like global maximum. And we have also like this valley of death where our solver, this math stuff, it's just stuck in the valley of death, so it cannot go up, and then we don't see any optimum numbers. Um, and we simply say like it's not converge or it's not giving any solution, right? That can happen as well. But then more than two variables, we will not be able to see this nice graph, right? We will not be able to see this nice graph. So for that, then we will have to rely on the solver capability. What I mean by solver, I think I missed that. What I mean by solver was that previously, if we have like x, we have that some initial x value. Either we start from here or from there, or from here, from there. It doesn't really matter. And then what is then the next x? Yeah, so to get from one x to the next x, that is then the job of a thing called solver. So that solver can use like gradient based method or like a trial and error or this combinations of both. So that's basically what that means if I try to explain it in a simple language. So once we get that model right, and then in some cases we do like ad hoc simulation optimization, right? So we just make a model and then we use it ourselves. So then we know where the model can go wrong, and then what inputs are not correct, and then how to analyze the results. So some ad hoc, some cases that we do ad hoc simulation optimization. But then in most cases, we build the software, that model or the tool or NAP, whatever we want to say, whatever we want to call it. So once we build that application, we will have to then hand it over to a different team where they do some, I don't know, some optimization with it. So they do some calculation with that. So in that sense, we will have to make sure that that application is that user friendly. It's intuitive to navigate. It also has some features where users can then select their own preferred solutions and then just to compare it, make some comparison. It has to have like some data set and training materials, and then you also have to have some IT support in terms of like data flow. So because we know all of these models are nice to have, right? But then the value comes when we can make good decisions from that model. So how do we make a good decisions if we assuming that the model is running well? So the only thing that matters is then make sure that the input is well defined. So it's we don't give in the correct input, and then we only give like acceptable input and acceptable scenarios. Then we put these inputs into the model, and then we can get some meaningful results. And then the next day or the next period, we do another scenario or we make another case adjustment. So and then we can then compare the results. So all of this will not be happening smoothly if we don't have like the robust infrastructure on the data itself. So I just simply took this as an from the article as an how to call it, as an illustration on how important data infrastructure is, because as we all know, if we put garbage in and then we'll get garbage out, right? So enough with all of these process engineering stuff, mathematical modeling, and then see data infrastructure. So I'll just share with you a few things that I've done in the past that is aligned with this. So We do something what we call like plant-wide optimization or real-time optimizations, or what do you want to call it. So assuming that this is your plant, right? And then this plant has many recycles, and then there are few things or few approaches that you can use to solve this. But I just took this example where we have a hybrid modeling, where we have a first principle calculation, like we know we can do like a flash calculation in the tank. We have pump equations, we have heat exchangers equations, we have like kinetics in the reactors, and then some splitting and then mixings, some pressure drop in the valve, and so on and so forth. So these are like first principle equations that we know what the model is. But then for things that are difficult to converge or relatively difficult to converge, or things that we don't know how it performs basically, but we do have data for that. Or for example, in this distillation column, it's relatively not so easy to converge, and then but we do have some data, and then we can run this several times to get enough data so that we can make our like a neural network architecture with that. So this software enables us to do so. We have a hybrid environment where we can jointly connect we can connect the first principle equations on this part of the model, and then this neural network architecture in this distillation column and in that distillation column, and then this stream, right? This is then the results of these neural network equations. Then it can be sent back to the flash tank as another stream. So I cannot make a demo, but just you have to believe me. So with this, even though this is simple, we have the kinetics, but we have some recycles. Simulating with the actual distillation columns over here and over there, it will we will be fair. I mean, we will experience unconvergent situations, let alone if we want to, and it's also not relatively not easy to solve, and it's also like let alone that we want to optimize the performance of the plant, right? So we have two obstacles there, the unconvergent the convergence issue, and then the finding the optimum solution. But then with this hybrid feature, this neural network is simply like a regression, so to say, so it's very easy to solve. So if we have this type of system solving this, right, configuration is much faster, and it's guaranteed to be solved anyway, compared to the distillation column where we can find this unconvergent situation. So that's a tool that we can use, yeah. So a hybrid between the first principle and then the some regressions to account for I mean to overcome this non-linearity and then the recycles of in the system. So that's one example on the in this aspect. And then there's also another example, say for example, for the production planning of refinery or any chemical plants or any processing plants. We know that we are going to source our raw materials somewhere from somewhere using any type of mode of transportation, and each of these options they will come with different costs, right? And then when it gets to our processing plants, they will then be processed to make some other products which are more valuable, and then they will then be transported by using different mode of transportation to different locations. That also carries variations of cost. So the question is then, okay, which crude or which raw materials that we are going to buy, to which plant are we sending them, with which operational mode that we are going to process or make a product, which products to produce, and then which customer to serve. So all of these questions, we can then model that, and then simplify the equations or the performance of the plant in such a way that we can have like a high level planning system, like in this case enterprise web planning. So I took from, I don't remember what this paper, the title of the paper, but then you can find it, I think, in like RTO or something. um, so if we go down this hierarchy, we will then go deeper and deeper into the plant and up until this regulatory control, or what we call this basic process control scheme, BPCS, basic process control scheme, right? And then if we go up, it's more on the planning for enterprise-wide or complex-wide, or yeah, whatever you want to call it, basically. So an example for that, I think this is a typical example for refinery planning, and we have some equations for this. So profit equals to income minus raw material cost and then minus processing cost. So we know the cost of the and then we know how to calculate the income, right? So so by selling the product, So the flow of the product, which we don't know, but the product price we know. And then it also comes with some uncertainty. So that's where the art comes into picture later on how to use this to make some cases and stuff like that. And then raw material cost, similarly, it's just about the crude flow, and then we just need to know which crude that we're going to buy and how much. And then they come with the cost, and then some processing costs. So different type of crude will then come with a different processing cost because some is then heavy, some is then lighter, some is then I don't know has lower impurities and so on and so forth, right? So we are limited by also by the processing capability of the plant, and then the job is then to find, okay, which crude to buy, and then which I think they have like which to buy, and then which yeah, process it, yeah, how much, right? Which crude to buy and how much. And then we make it like I think this software, it has some capability to do so for the planning, and then it's well documented in this example as one example, one of the resources that I think we could read. Another application is what they call like network optimization. It works the same way or similarly with that this production planning stuff. But in this case, as opposed to like getting into the picture of the processing facilities, how the product is, how the raw materials are processed into products, it deals more on this side of the diagram. So we have different raw materials and then different locations, and then we have different locations of our plants, and then which crude that we should buy using which mode of transportation, and then to which refinery or which plants, yeah. Or we can also see it from this angle, just a matter of transporting chemicals from one place to the other, right? And then these are like the yeah, I'm not going to into details on the math formulation for this, but you can see it. And the goal is then to know, okay, what's then the cheapest cost to supply from different locations to another locations. And if we get to deploy this, so I put like a dummy case here. So these are some some locations, some cities in Java Island in Indonesia. So we have different plants with its own like capacity, and then we know that we can use all three of them, for example. That's why this three checkbox are there. And then we have some like intermediate storage location or distribution center, how we call it. So different locations as well with different capacity. And then we have like different customers that we want to satisfy. This is then their demand requirement, and then they are all active, means we have to supply them. And then these are some of the cost factors from one location to the other, from factory to distribution center. This is then the cost from distribution center to the customer demand. All of these are the input data that we have to verify, right? And then we have to check. Say for example, just put a dummy case. So I have like three plans with me, and then I have these customers to for whose demands I'm going to fulfill. And then I'm thinking on where to put my distribution center. And then I have like three options, right? Three options, because now I don't know where to put, just three options, and then each with their own capacity limits that I can think of, and then they have their own cost associated to it. And then we can then click solve, and then it will give us, okay, so you would need apparently all of these three, but then with these three distribution center, you would need then to send 200 to Tasikmalaya, another 800 to Surakarta, and so on and so forth. And then from the same distribution center, you will need to send the other way around. So to Cikarang distribution center will then supply it from our plant in Tasikmalaya and Surakarta. So from here, 200 from Tasikmalaya and 800 from Surakarta. And then similarly from the Cikarang, if we want to fulfill the demands of these, and then it will then have to serve this Bandung 450, Semarang 450, and then Malang 100. And then this is then the total cost of supply. And there's then the yeah, I mean the some visualizations on how the goods are flowing from one location to the other, and then we can then evaluate. Say for example, this is too small, so I may need to emphasize or make some other constraints to make this zero, and then give everything to Sidoarjo because it's much more convenient for me, and so on and so forth. So you could do all of this scenario analysis and then some case studies. So this is what we call like in this network optimization. Yeah. So this is then the I think the third example, right? And then the fourth example is more like this is an energy transition period or whatnot. This whole hype. So we take into account like some electricity consumption in different countries, especially now in Indonesia, for example. So we know that we have a list of sources of energy production, like the supply, and then we know what each region has in terms of the coal, natural resources, natural gas resources, and so on and so forth. And then they are going to be used to produce electricity. Yeah, and this electricity will be used for different regions and then different amount of demands in this category. So we collect data for the supply part, and we also collect data for the consumption part, and then we take into account like the growth we assume as percentage of growth every year, and then we do some planning. The goal is then to make sure that we will try to meet these demands every year in such a way that we will then try to minimize the CO2 emissions, so that we will need to know which plants that we want to build in which region, and then how big is that plant, in such a way that we can keep up with the demand but still minimizing the CO2 emissions, or put the CO2 emission as a constraint, but minimizing the cost. Yeah, so we could do all of these studies, and we modeled it, and then we deployed it in the same software platform. So we have just dummy case, so region A, B, C, D, and so on and so forth, and then we can also allow it to supply. Yeah, so for example, region A has more oil compared to region B, so this oil can be transported to the region B, and then region B then can then make their own or generate their own electricity, for example. And then they have like initial demand and then some demand growth, and then we have different technologies that can be installed in different regions, and then the yields of the electricity or the products, for example, and then some costs related to it and some CO2 emissions related to it. These are all like dummy numbers, but I think you get the point. Now, when we run it and then let the solver does the work for us, does the thinking for us, and then we can see, for example, so in these regions, B and C, for example, we will need to have technology A, B, C in this 2020 starting point to fulfill that demand. And then as we move along in these years, we know that, well, this region B, we will need to have another technology C installed in 10 years from now, for example, right? And then in this region C, we will need to have this technology B installed in 15 years from now. So there we can see what's going to happen and then how it happens, as such that we still meet the demand requirement, but we also obey the other rules and regulations that are applicable for this in this situation. Another example is on suppose that we have various projects that we want to fund, but we have some limited number of funds, and then we also have some limited fund sources, right? And then I'm not going to bore you with the math, but then that's how we formulate that. And then at that time we put it into Excel because it's Excel solver is strong enough already with this small list. So we take into account the S-curve of the project, and then some math into it, and then we deploy it somewhere here, and then we have different projects that we can we know we can prioritize them. So I put them all blank here, but nonetheless we have this I think this then the capex, and this then the NPV. So obviously we want to have the highest NPV with the lowest capex, right? So this part is then our favorite part, the higher NPV and then the lowest capex. But then taking into account this whole S curve, and then we can then see or make priority and then we can then select, add some more subjective intuition into the decision making, but we are already equipped with some baseline to draw some conclusions, and then we can make different cases. So either we take into account the progress of each of the project, or we just simply try to see how it's going to look like if we maximize the capex, or minimize the capex, or maximize the NPV, and so on and so forth. Yeah, so that's how we deploy the tool. Another one, I think the last one. So I did this some long time ago. So it's more like an undergraduate project, right? So we have like various titles proposed, and then the students have to pick, like, I don't know, one, two, three, and then they will then have to pick three titles each of the student, according to their preferences, right? So this student, for example, 22306, it will then select this project mode 3 as his or her first preference, and the second one is experiment 13, and then the third one is experiment 7. So all of these, they do it, right? So we just put them a form, and then they will fill it. And then the goal is that, because I mean, one project can be interesting for more than one student, right? That's why we do this. So to account for the whole happiness level in the in the batch or in the class, we make this, and then we model that in such a way that we maximize the happiness in the whole batch, right? So what comes after that is that, okay, so these students, it will have to take these titles, both or one, and then these students will take this experimental twin, and so on and so forth. So if we calculate the happiness index for this, it's the highest, yeah, compared to other solutions, maybe. Yeah, but at least with this we know, and then we can say, well, to the student, we can explain to them, if you pick this and pick that, and then you have the second option, which is I don't know, maybe more beneficial, or maybe more preferred for you, all kinds of arguments that we can make. But at least we can then objectively decide which project that we're going to assign to which student based on their preference, to maximize the overall happiness of the students. So I think with that, I end my presentation. So if you have any questions, just let me know.